In this video, we'll be sketching the gradient functions, or rather, sketching the f dash or the derivative or the first order derivative function. Okay, so let's get to it. Let's say we've got this shape of a graph and we have to sketch the derivative function. We notice that there are actually three turning points there. Notice that wherever you can draw a tangent line, and this tangent line is horizontal line parallel to the x-axis. That's a turning point. That's how you identify turning points. Alright, so then how did I identify these vertical lines here? Because we briefly said that whether wherever we can draw a horizontal line that's tangent to the graph, that's where we have a turning point. So at those turning points, it's usually norm just to make your life easier, draw another x and y axis directly under it and just use a ruler to project those lines down here. Project those x values down on this gradient function curve. Now you're going to look at the guess the shape or the of this graph from what you learned in chapter 3 and 4. Chapter 3, yes, chapter 4 actually, when we plotted the curves. This is a negative quartic graph. Now that means that because of the three turning points, there has to be something to the power of 4, and it has to have a minus sign there. And when you differentiate, this is our original f of x here, and when we differentiate that, I'm having a guess here. Of course there is some value of a there, and there is some other terms, okay, but the most important part of the function is this, the highest power of x. So this will be a negative 4a x to the power of 3. The point is, we almost don't care about this 4a there. The point is that it's minus and it's a cubic. The f dash of the f dash or the derivative function is negative cubic, therefore it will have an end there and end there. That's what I'm trying to get to. So it will come down here, cross this point, make a U-turn here, and make yet another U-turn, and make go off into infinity. Now, how do I know that this is a U-turn here? Because I have briefly in this interval a decreasing interval. Alright, so it's the derivative must be below zero, below the x-axis. Why is this is representation of f dash, okay, and here it must be positive because between this interval, these two x values, it's increasing, and then it goes and becomes decreasing again. So notice that here the graph from minus infinity up to this x value, the graph is increasing. That's why this part of the graph is above the x-axis. The y value of it is positive. So it will look something like so. So we just don't want to fast forward too quickly. So we said that it had a gradient on this side is gradient is negative and decreasing. Okay, so let's look at this next example. We want to read the question carefully. Alright, in all cases, should really read the question first. It says that it has a stationary point at x equals to minus 1. It tells us already we don't know what the function is. Perhaps we don't have time to work with that, but we know there is one turning point here where I'm putting a dot, and there is another turning point where I'm x equals to 1. Clearly it's told us those 2 points. And it tells us that it cuts the x-axis at minus 3. So we know this is a positive cubic. If we wanted to figure out its equation, we would have multiplied this out and we could get the equation. But we actually don't, maybe we don't have time for that. So we just have to go straight to the point and sketch the gradient function under it. So just project those points where you have turning points and project them down onto not the x and y axis where the y axis line up neatly with each other, and we know that this is a positive one and this is a minus one. X has to be labeled those 2 points there. And what are you going to do? This is a positive uh, cubic here. So positive cubic, if I have a plus ax to the power 3 and of differentiate that, I'm going to get positive a quadratic, right, as a derivative. So this is f of x, and I differentiate that f dash of x is positive quadratic. So I'm going to have a smiley face here. And you can guess that if you just draw yourself a smiley face there, you notice that you've actually plotted it correctly in this interval between -1 and 1. It should be below x-axis, and whenever it's less than -1 it should be positive because it's increasing here in this interval. The original function is increasing and it's again increasing anywhere to the right of 1 there. Now, does it matter what that coordinate is? No, it doesn't really, but we could find it if we wanted to. So here we go. This is the original function. If we wanted to know what that intercept is, we would have found the f dash of x is 3x squared plus 2x minus 5, and that point would be a minus 5 y coordinate of turning point. So how did I do that? I multiplied out these terms and added the like terms together. I hopefully did that correct. Yeah, and that's how I would have found that. So now in this next example, taking this example out of the book, so we've got a turning point at minus 3 x coordinate is at minus 3. That's the only turning point we have. We have a horizontal asymptote on the graph, and that doesn't matter what the horizontal asymptote is, to be honest with you. What matters is that where that turning point is, we're going to have a zero on the graph. Okay, so this is a same graph. Yeah, so at my x equals to minus 3, we're going to have a root here at x equals to minus 3. So you think about it, the function is decreasing up to x equals to minus 3, so it should be below the axis, below x-axis, and then after negative 3 it turns positive, it's increasing, so that's why the derivative function is above the x-axis. Now, the fact that it has an asymptote and is reaching an asymptote means that its gradient is going towards zero, and because it's approaching its zero from below, so it was positive and it's turning into zero. So that's why it's positive and the gradient is turning towards zero as well. Okay, so I've taken this out of your exercises. It's sometimes confusing why this x equals to 6 is a vertical asymptote there. Therefore, your gradient sketch should have an asymptote of x equals to 6 also, and that's exponential curve. We will meet that in a couple of chapters time in chapter 14, and it will have almost a similar gradient. We don't know anything else about it, so we can't say anything more. This Wirth is at -7, therefore the gradient function is at -7. Now it's always decreasing here, so the graph will be always below x-axis because any value of x less than -7 has a negative gradient, and it should be. That's why our line here is also always below x-axis, and it is decreasing up to 4. 4 is the point where it kind of flattens out, it meets the x-axis and then turns back to negative. It becomes more and more negative, so we send the gradient down below, and so on. It's something that it's more of an art drawing these kind of gradients. This is was like a positive. Try to have a guess at the curve. What's the function of the curve? Its highest power is a cubic, so the gradient function should be quadratic. Is a positive quadratic. Here is a negative cubic, so therefore the gradient function will be a negative quadratic. Alright, so you know when you differentiate, the powers go down, therefore the highest power will be one less for the gradient function. It shouldn't be a surprise for you. So have a go at this exercise, and I will see you in the next video.